Golden Iris Productions presents The Hidden Rhythms of the Hydrogen Atom, Wave Structure, Quantized Motion and Photon Emission by Mark F. Dennis.
Part 3.
Abstract. The development of modern atomic physics emerged from a sequence of foundational discoveries spanning the electron, proton, quantized radiation and matter-wave duality. Beginning with the identification of subatomic structure by J. Thomson and Ernest Rutherford, and culminating in Bohr's quantized atomic model, a new framework of discrete energy states replaced the classical continuous description of matter. Concurrently, Planck's resolution of the ultraviolet catastrophe introduced energy quantization through E equals h nu, later extended by Einstein's photon hypothesis, establishing the quantum nature of electromagnetic radiation. De Broglie's matter-wave theory further unified these developments by proposing that all matter exhibits wave-like behavior governed by lambda equals h over p. This work presents a consolidated historical and theoretical foundation of quantized atomic structure, emphasizing the emergence of discrete electron shells, standing wave conditions, and photon emission as interconnected consequences of wave-particle duality.
Introduction. The discovery of the electron by J. Thomson and the subsequent identification of the proton through the work of Ernest Rutherford fundamentally transformed the understanding of atomic structure and established the foundation of modern atomic physics. Prior to these discoveries, the atom was widely regarded as an indivisible unit of matter. However, experimental evidence demonstrated that atoms possess an internal structure composed of charged constituents. Building upon this framework, Niels Bohr proposed his atomic model in 1913, introducing the revolutionary concept that electrons occupy discrete, quantized orbits around the nucleus. Within this model, electrons may transition between allowed energy levels, emitting or absorbing electromagnetic radiation, whose energy corresponds exactly to the difference between initial and final states. This provided the first successful theoretical explanation for the discrete spectral lines observed in hydrogen, and established that light emission from atoms is a quantized process rather than a continuous classical phenomenon. At approximately the same time, classical physics encountered a fundamental crisis in the form of blackbody radiation, known as the ultraviolet catastrophe. Classical theory predicted that a heated object should emit infinite energy at short wavelengths, a physically impossible result. In 1900, Max Planck resolved this paradox by proposing that electromagnetic energy is exchanged in discrete packets, or quanta, with energy proportional to frequency, E equals h nu, where h is Planck's constant, a fundamental constant of quantum mechanics. This result demonstrated that energy is not continuously divisible, but instead exists in discrete units.
Planck's hypothesis unexpectedly revived aspects of Isaac Newton's earlier corpuscular theory of light. Although wave theory had been firmly established in the 19th century through the work of Thomas Young and James Clerk Maxwell, Planck's quantization suggested that electromagnetic radiation also exhibits particle-like behavior. This duality was confirmed by Albert Einstein in 1905 through his explanation of the photoelectric effect, in which light is treated as discrete localized quanta, later termed photons. This established that electromagnetic radiation is neither purely wave nor purely particle, but fundamentally quantum in nature. Together, Bohr's atomic model and Planck's quantum hypothesis revealed that light is produced through discrete electron transitions governed by quantized energy exchange. This marked the beginning of quantum theory and fundamentally reshaped the understanding of physical reality. With light now understood to exhibit both wave-like and particle-like properties, physics entered a deeper conceptual transition. In 1924, Louis de Broglie extended wave-particle duality by proposing that matter, previously considered purely particulate, also possesses wave-like properties. This hypothesis is expressed by the relation lambda equals h over p, where the wavelength lambda of a particle is determined by its momentum p and Planck's constant h.
This proposal implied that every moving particle is associated with a wave, and for the electron, this wave-like behavior provided a natural explanation for the quantized orbital structure first introduced by Bohr. The Bohr model had already demonstrated that electrons in the hydrogen atom occupy discrete energy levels, or shells, labelled by the principal quantum number n. Each value of n corresponds to a specific allowed orbital radius. The ground state, n equals 1, defines the Bohr radius, A0, approximately 5.29 times 10 to the minus 11 meters, which sets the fundamental scale of atomic structure. Higher shells follow the relationship R sub n equals n squared A0, demonstrating that orbital radii increase rapidly with increasing quantum number.
What Bohr introduced as a postulate finds a physical interpretation through de Broglie's wave mechanics. The electron is permitted to occupy only those orbits in which its matter wave forms a standing wave around the orbital circumference. This condition requires constructive interference, expressed as 2 pi Rn equals n lambda n, ensuring that only integer wavelengths fit around the orbit. If this condition is not satisfied, destructive interference prevents stable orbital formation.
In this way, quantization merges naturally from wave behavior, rather than being imposed as an independent rule. This wave-based interpretation unifies Bohr's atomic model, Planck's energy quantization, and Einstein's photon concept into a single coherent framework. When an electron transitions from a higher to a lower energy level, its standing wave configuration changes, and the resulting energy difference is emitted as a photon, governed by E equals h nu. In this formulation, light arises from the reconfiguration of stable matter wave states. The hydrogen atom, therefore, represents the first physical system to demonstrate that matter and radiation are governed by the same underlying quantum principles, in which discrete atomic structure and discrete light emission are two manifestations of wave-particle duality.
Transition to relativistic structure. During the early 20th century, while quantum theory was emerging, Albert Einstein was developing a fundamentally different but equally revolutionary framework, general relativity. Einstein sought to describe gravity not as a force acting at a distance, as in Newtonian mechanics, but as a manifestation of space-time curvature induced by mass and energy. The mathematical formulation of this theory required an entirely new description of geometry and dynamics, and its development occupied Einstein for several years during World War I. At the same time, Karl Schwarzschild, serving on the front lines of the war, obtained Einstein's field equations and derived the first exact solution for a spherically symmetric, non-rotating mass. Despite the extreme conditions of his service, Schwarzschild successfully obtained a complete analytical solution and transmitted it to Einstein, who was reportedly astonished by the result. Schwarzschild geometry and gravitational time dilation.
The Schwarzschild solution represents the first exact solution to Einstein's field equations for a spherically symmetric, non-rotating mass. It is one of the most important results in gravitational physics, providing a precise mathematical description of space-time curvature in the presence of mass. A central consequence of this solution is gravitational time dilation, expressed as T prime equals T divided by the square root of 1 minus 2gm over rc squared, where g is the gravitational constant, m is the mass of the gravitating object, r is the radial distance from its centre, and c is the speed of light. This expression demonstrates that time is not absolute. Instead, the rate at which time passes depends on gravitational potential. As an observer approaches a massive object, the rate of time progression decreases relative to a distant observer. At the Schwarzschild radius, r sub s equals 2gm over c squared, the denominator approaches zero, causing the time dilation factor to diverge. This boundary defines the event horizon of a black hole, beyond which classical descriptions of spacetime cease to apply in a conventional sense.
Physical interpretation of spacetime curvature. The Schwarzschild solution represents a fundamental departure from Newtonian physics, in which time was considered absolute and universal. In contrast, general relativity demonstrates that spacetime is dynamic and deformable, with its structure determined by the presence of mass and energy. Time is therefore not an external parameter, but an intrinsic component of the physical universe, coupled directly to matter through the geometry of spacetime. Historical context and significance. The significance of the Schwarzschild solution is amplified by its historical context. Karl Schwarzschild derived this solution while serving on the front lines during World War I, having obtained Einstein's field equations shortly after their publication. Despite extreme conditions, he succeeded in obtaining the first exact analytical solution to the equations of general relativity. Schwarzschild transmitted his result to Einstein, who was reportedly astonished by its completeness and elegance. Schwarzschild died shortly thereafter in 1916, but his work permanently transformed gravitational physics. Toward an electromagnetic analogue of spacetime curvature. The Schwarzschild solution demonstrates that mass curves spacetime and modifies the rate of time itself. This raises a natural question whether analogous relativistic effects may emerge within bound electromagnetic systems, such as the hydrogen atom. To explore this possibility, an electromagnetic analogue is constructed by mapping gravitational quantities to electrostatic counterparts. The gravitational constant g is replaced by Coulomb's constant k, and the gravitational mass m is replaced by the electron charge magnitude, where q equals e. The electron's inertial response is governed by its rest mass me, which appears in the denominator as a moderating factor. The characteristic length scale is taken as the Bohr radius, a0, while c remains the universal limiting velocity. This leads to an electromagnetic analogue of the Schwarzschild time dilation expression. T prime equals 1 over the square root of 1 minus 2kq squared over 2me times a0 c squared. This formulation suggests a formal structural analogy between gravitational space-time curvature and electromagnetic confinement at atomic scales, where charge-based interactions produce a curvature-like modification of temporal scaling within bound quantum systems. Electromagnetic time dilation and atomic scale relativistic structure. This expression suggests a significant extension of relativistic interpretation. Time dilation may not be exclusively a gravitational phenomenon associated with macroscopic masses, but may also emerge from intense electromagnetic confinement at atomic scales. In this interpretation, the electron's charge produces an effective curvature-like structure that modifies the temporal evolution of its bound state. Analogous to the Schwarzschild solution, where time slows in the vicinity of massive objects, the electromagnetic analog implies that temporal dilation arises in regions of extreme charge density interaction.
Atomic scale interpretation of temporal modification. At the scale of the hydrogen atom, this effect is subtle but mathematically well defined. The Bohr radius represents the minimum stable orbital scale, where electrostatic confinement is strongest and electron velocity is maximized. Because the electron exists simultaneously as a localized particle and an extended matter wave, confinement within this region reflects both spatial restriction and an associated modification of temporal evolution. As the orbital radius increases with higher quantum number n, the effective electromagnetic curvature weakens and the associated dilation factor approaches unity in a manner consistent with reduced acceleration and orbital velocity.
Quantum relativistic coupling interpretation. This framework provides a conceptual bridge between quantum mechanics and relativity. Bohr introduced discrete orbital shells as empirical quantization rules. De Broglie provided a wave-mechanical interpretation in terms of standing matter waves. Einstein and Schwarzschild demonstrated that energy and mass distribution influence the structure of time itself. Taken together, these results suggest that the electron's quantized states may reflect not only spatial resonance conditions, but also temporal resonance conditions. In this view, allowed atomic states correspond to configurations in which wave closure and relativistic temporal consistency are simultaneously satisfied. Atomic system as a relativistic oscillator. If this interpretation is correct, time dilation becomes an intrinsic feature of atomic structure rather than solely a cosmological effect. The hydrogen atom may therefore be interpreted as a natural relativistic oscillator in which charge, inertia, and wave resonance combine to produce discrete temporal states. Within this framework, photon emission during electronic transitions corresponds not only to a change in energy and wavelength, but also to a transition between distinct local temporal geometries. This provides a unified interpretation in which Bohr, de Broglie, and Einstein contribute complementary aspects of a deeper underlying structure: quantized matter as resonance within curved spacetime. Electromagnetic time dilation across hydrogen shells. Evaluating the electromagnetic Schwarzschild analog for the first 6 hydrogen shells yields the following time dilation factors. Gamma n equals 1.00026622, 1.00006655, 1.00002958, 1.00001664, 1.00001065, 1.0000739. These values exhibit a monotonic convergence toward unity as the principal quantum number increases. This behavior follows directly from the inverse relationship between confinement and orbital radius. At n equals 1, the electron experiences maximum electrostatic confinement, maximum acceleration, and strongest effective curvature. As n increases, the orbital radius scales as n squared, reducing confinement strength and causing the dilation factor to asymptotically approach unity. Physical interpretation of temporal hierarchy. Although the deviations from unity are numerically small, their physical significance lies in interpretation rather than magnitude. In relativistic theory, any deviation from unity represents a modification of local proper time. The ground state factor, gamma 1, equals 1.0000266622, implies that time within the most tightly bound electron state evolves at a slightly different rate relative to an unbound reference frame.
This is consistent with Einstein's principle that energy density modifies space-time structure. The hydrogen atom therefore exhibits a nested hierarchy of temporal states, where each shell corresponds not only to distinct values of radius, velocity, acceleration, and de Broglie wavelength, but also to a distinct local rate of time evolution.
Electron transitions as temporal reconfiguration. Within this framework, electron transitions acquire an extended interpretation. In the standard quantum description, transitions between shells produce photons whose energy corresponds to the difference between quantized energy levels. Here, photon emission is additionally interpreted as a transition between distinct temporal geometries. The emitted photon represents not only a carrier of energy, but also the observable consequence of a change in local proper time structure within the atom.
Ununification perspective. This perspective provides a conceptual synthesis of key developments in 20th century physics. Bohr established discrete atomic structure through quantized shells. De Broglie explained these shells as matter-wave resonances. Einstein and Schwarzschild demonstrated that energy influences the structure of time. Together, these results suggest a deeper possibility. Atomic quantization may arise from resonance conditions that couple matter, energy, space, and time into a unified constraint system.
Hydrogen atom as a fundamental relativistic clock. If this framework is valid, the hydrogen atom may represent the smallest naturally occurring relativistic clock in the universe, where quantum mechanics and space-time geometry converge in a single self-consistent structure. Wave closure and boundary conditions. In extending this interpretation, the de Broglie wavelength is not merely a geometric property of orbital motion, but a direct manifestation of the standing wave boundary condition of the bound electron system. Each allowed shell corresponds to a resonant mode in which the electron's matter wave satisfies an integer wavelength condition around the orbital circumference.
Quantum transitions and photon emergence from standing wave reconfiguration. From the wave-based perspective, a quantum transition between atomic shells can be understood as a reconfiguration between two distinct standing wave states of the electron. When the electron transitions from a higher energy level to a lower one, the system must shed the excess wave structure required to satisfy the boundary condition of the initial state. This change is not arbitrary, it is quantized and corresponds to a discrete modification of the allowed standing wave configuration of the electron.
To be continued.